Welcome. In this video, we're going to talk about the directional derivative and how it plays a role similar to that of an ordinary derivative when we want to estimate how much the value of a function f changes. If we just move a very small distance away, and we'll call that distance ds as in a differential. All right, so if we move just ds or delta s away from some point, we could find the derivative, and we're just thinking of a regular function with one variable. It would be f prime from that point, f prime of p naught, and then we've got this ds. Okay, so this is the same as writing that equation like df ds is the derivative at that point. So multiplying it. Well, let's think about what this means. We have our regular derivative, and then we have this increment here, a small amount, a distance away. Now, if we were doing this with a function of two variables, that would end up looking like this new calculation. We would take that gradient, evaluate it at the point, dot it with my direction unit vector, times again that ds, there's my increment. So instead of the regular derivative, we now have this directional derivative. All right, so up there we would say, well, that was our regular derivative times some increment. Here we have a directional derivative times some increment. So as we talk about estimating the change in a function in the direction of u, to estimate that change, as long as it's differentiable and we're moving this ds, this small distance away from the point in the direction of u, we're going to use this formula here. And so why is this useful? Well, it's useful because we want to estimate the value of a function, and if we just are a tiny bit off, how much would that really change? And so if you start thinking about, we'll think about regular calculus, a tangent line, right? So over here on the right, the further I move from that point, I'll call it C here, I could call it P naught, but the further I move from the point, we see there's much more error. But if I'm just a tiny bit off, is there really going to be much error or change in that derivative? And the answer is no. All right, so let's look at an example where we estimate change, and then we'll talk about linearization. So for this example, we're going to estimate how much the value of this function, y times sine of x plus 2yz, how much it will change if that point, the initial point, moves a tenth of a unit from 0, 1, 0 in the direction straight, and I realize that's written wrong, I'll fix that in a second, straight toward p sub 1, which is 2 to negative 2. Okay, so what should we do? Well, the first thing we're going to need to do is to find that first derivative. So step one, we're going to find the derivative. The derivative of the function at, that's a weird looking at p naught in the direction that we are moving. And which way are we moving? And that would be the vector from p naught to p sub 1. So what is the length of that vector? P naught to p sub 1, that's going to be the difference of my x values, 2 minus 0, 2 minus 1, and negative 2 minus 0. So that gives me 2I plus j minus 2k. So that's the vector, and we just want the direction, which means we want to turn that into a unit vector and divide it by its magnitude. So the magnitude here, the square root of 2 squared plus 1 squared plus 2 squared, square root of 9 is 3. So that means my unit vector, my direction, or u, is going to be 2/3 I plus 1/3 j minus 2/3 k. So there's my unit vector. So also, in order to solve this problem, we need that directional derivative. So I need to find the gradient here so I can dot it with this unit vector. So as I go to find my gradient, and I brought my function down here, I'm going to find that gradient and I need to evaluate it at the initial point, 0, 1, 0. So I need the partial of this function with respect to x. That means y is a coefficient. This term will go to 0. Derivative of sine is cosine. So I have y times the cosine of x. I. Partial with respect to y, that means sine x is a coefficient and 2z is a coefficient. So I have sine of x plus 2z j, and then the partial with respect to z, 2y is my coefficient, so I'll have plus 2yk. Now, I still need to evaluate this, and I ran out of space over here, but I need to evaluate that at my point 0, 1, 0. So I'll plug that in, and I have 1 times the cosine of 0, which is 1, so I've got 1i. Sine of 0 is 0, plus 2 times 0, I've got plus 0j. And 2 times 1, I have plus 2k. So simplifying that, that's just going to be I plus 2k. So that is my gradient of f. So I need to take this gradient of f and dot it with u. So the gradient of f at my p naught, which needs to be dotted with my u vector. My u vector up here was 2/3 I plus 1/3 j minus 2/3 k. So we have I plus 2k dotted with 2/3 I plus 1/3 j minus 2/3 k. And that dot product gives me 1 times 2/3, 2/3, 0 times 1/3 is 0, and 2 times negative 2/3 gives me negative 4/3. So this simplifies to negative 2/3, which this here provides my directional derivative. So the formula that we stated was that df is that directional derivative, gradient f at the point dotted with u times this small estimate or prescribed error, if you want to think of it that way, this differential of distance that we may be off. So how far away did we move? We moved 1/10 of a unit away. So that 1/10 is going to represent my ds, and that means I'm going to say df is negative 2/3 times 0.1. So negative 2/3 is negative 0.6 repeating times 0.1. And so what that does is that moves the decimal over 1 place. So we will be off by negative, essentially, 66 thousandths of a unit. And so we can visualize what's going on here. Here was my surface, and this is my gradient coming out perpendicular, And essentially what this is saying is if we move 1/10 from that initial point, 1/10 of a unit this way, that differential change, the df value, recall this is equal to df. And so df represents a change in the function. And that results from moving this ds quantity 0.1 unit away from the initial point in the direction of u. Okay, so that change is approximately 67 thousandths. All right, so we'll follow this video beginning to talk about linearization. All right, email me if you have questions.